times. All right, okay, so today we're going to take a look at the beta binomial model. We're continuing on our discussion of kind of introductory Bayesian concepts here. All right, and so so on Monday we talked about the beta distribution, and we said, well, the beta distribution just has this PDF here, okay, and so you know, it's 1 over beta alpha comma beta times theta raised to the alpha minus 1 and 1 minus theta raised to the beta minus 1. The only part of the function that really, you know, kind of changes to theta is this part over here, okay? Where anything, where this part, okay, beta alpha comma beta, you know, it's got a complicated formula using gamma functions, but it's effectively a constant, okay? It's a constant, and its purpose is so that the integral of the entire PDF, if we integrate it, it's going to integrate to 1, okay? And so, you know, what we can do is we can just rearrange a few terms, and we can say, well, you know, we know that the PDF is defined for the beta distribution. The PDF is defined from 0 to 1 because, and it's used frequently to kind of model random probabilities or random proportions. Okay, so we know that the PDF integrates to 1. And because we know it integrates to 1, and we know that this is a constant, okay, with a little bit of rearranging, right, I can pull out this constant from this integral, and we can say that this constant times this integral is equal to 1. And therefore, if I move this to the other side, we can say that if I just integrate this portion, okay, if I integrate this portion, this integral has to equal this value here. All right. The screen is not on the notes. What is the screen on? It's on me. Oh, geez. Oh, yeah, I'm not sharing. Okay, well, my bad. That's embarrassing. Is it now on the notes? I can't tell. You can see them. You were able to see the notes. I'm sharing the entire screen. Same here. Okay, it's been on the notes there too. Okay, all right, somebody, okay. Okay, all right, well, I don't know. It's been on your slides. Okay, all right, all right. You know, so I have, you know, the presenter doesn't get to see what the students are seeing, and so I'm just assuming that I'm doing this right, but yeah, okay, all right. The notes are shared, and we also see the rest of the screen, and the rest of the screen, like this, right? Like, okay, well, anyway, I can see you guys over here, so thank you for turning on your cameras. I like seeing your faces. I think you can see each other's faces too, right? And that's always nice. So anyway, just I'd like to encourage you to turn on your cameras. Okay, so anyway, is this okay, this relationship? We're going to say that the integral of this thing is going to be equal to this, all right? And this is kind of just, we're just taking advantage of the fact that we know that this is the PDF and that PDFs have to integrate to 1. Okay, and so this relationship will be useful for us later. Okay, let me go ahead and give you your first quiz answer. First quiz answer is the letter A as in apple. A as in apple is your first quiz answer for today. Okay, A as in apple, first quiz answer. Okay, and so we're going to continue looking at our example, our baseball example. And we said that, you know, in baseball, if you're looking at a player's batting average, pretty much everyone should have a batting average over 0.2, you know, otherwise they're going to get cut from the team. And it's you know, most players are going to have a batting average under 300 or under 0.3. And, you know, no one is going to have a batting average over 0.4, okay? And so, you know, we kind of, I arbitrarily picked these numbers of 81 and 219. Okay, and these are arbitrarily selected, but the resulting distribution aligns with our prior knowledge. Okay, so you could pick different numbers. It doesn't have to be 81 and 219, as long as you're kind of getting a distribution that fits this description where, you know, everything's going to be above 200. Most people are going to be under 300, and, you know, everyone, you know, no one's above 400. That's going to overall fit. That could work as a prior distribution, right? I'm using 81 and 219 because that's what shows up in that variance explained blog, and I'm just trying to be consistent with that. But you know, other numbers could work as well. Okay, and so if I create my PDF for this distribution, we're going to get something that looks like this. We're going to get 1 over the beta function alpha comma beta, theta raised to the alpha minus 1, 1 minus theta raised to the beta minus 1. And so I get 1 over beta 81 comma 219 theta raised to the basically 80, 81 minus 1, and 1 minus theta raised to the 219 or minus 1 or 218. Okay. And again, theta represents the player's batting average, and we can think of it as the probability of getting a hit. Go ahead and maximize this. Okay, and so what we're going to say is that let's say we get a new player. This new player has, we observe the player at 10 at-bats. So that's maybe a couple of games, 2 or 3 games. And in 10 at-bats, the player earns 5 hits in kind of the following sequence. And we get, we're going to say hits are 1s and outs are O's. Okay, so, you know, this, again, this is simplified, and, you know, in baseball, there's technically more outcomes based on balls, hit by pitch, things like that. But just for simplicity, we're going to say either the player gets a hit or an out, and we're going to also treat it as if they are Bernoulli random draws. Okay, and again, I know that baseball is more complicated, but just for simplicity, this is kind of what we're going to establish here. And so if we say we get out, hit, out, hit, et cetera, you know, this would correspond to X being 0, 1, 1, 0, 1, 0, et cetera. Okay. And the probability of getting this exact sequence of hits is going to be theta raised to the 5th, 1 minus theta raised to the 5th. Okay. If you wanted to just treat it as kind of a binomial probability, where you're just saying what's the probability of any sequence of getting 5 hits out of 10 at-bats, you know, then you would have a binomial constant, 10 choose 5 in the front. But it doesn't even matter, okay? And so, you know, just more generally, if we have a total of n observations and we have a total of z successes, so z being kind of the sum of our x values, then we would have theta raised to the z times 1 minus theta raised to the n minus z. Okay, so I think that's that should be fine with everybody, where theta is kind of the probability of getting a hit. All right, and so in Bayesian statistics, it's called Bayesian statistics because we use Bayes' rule. And so Bayes' rule is probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. And so we're going to establish this, or we're going to apply this to the situation that we're in. We want the probability, the posterior distribution. This is the thing that we want. We want the probability distribution of the parameter theta. Sorry, this should just say theta, not PR of theta. Okay, we just want the probability distribution of the parameter theta given the observed values in X. Okay, so given the X values that we have seen, we want the probability distribution of theta. And we're going to do this by taking the probability of X given theta. All right, and that's the likelihood. It's the probability of observing the observed data, of getting our observed data X for a particular value, given value of theta. So in our case, it would be, you know, what's the probability that we got 5 hits and 10 at-bats if theta is 0.2? what's the probability of getting 5 hits and 10 at-bats if theta were 0.3, okay, or if theta were 0.5, okay? So this is going to be a function based on theta. It's the probability of getting x for a given value of theta. So this is going to be a function of theta, and you know, our data is treated as fixed in the likelihood. This part, the prior probability or prior distribution of theta, okay, is going to be, you know, what we believed the distribution of theta was before we looked at any of the data. Okay, it's the it's going to be the prior, yeah. So for in our example, it is the beta distribution with shape parameters 81 and 219, but it could just be any kind of prior distribution is the prior probability distribution of theta. And then this bottom part is known as the marginal probability. Okay, it's the probability of getting your data regardless of what value theta is. Okay, so this part is a function. The likelihood is a function of theta, but this is just a constant. Okay, we're going to treat x, our observed data, as a fixed value, and so the probability of x is a constant. It's equal to, you know, taking the integral of the numerator across all possible values of theta. Okay, and this is just a constant. Okay, and because this marginal probability of x is a constant, the posterior distribution of theta can just be expressed as something that is proportional, that is going to be proportional to this. Okay, so I can just say it's proportional to the numerator, and I can kind of just ignore this marginal probability that shows up in the denominator because I just know it's a constant. Okay, so I don't need to worry about it too much. All right, so let's go ahead and plug in the values from our example. All right, we are saying that the likelihood function for observing a sequence of 5 hits in 10 at-bats is going to be excuse me, is it's theta raised to the 5th times 1 minus theta raised to the 5th. Okay, so this is the likelihood of getting that sequence of 5 hits and 10 at-bats. And then the prior distribution of theta, so we said before we even looked at how this player performed, we said the prior distribution of theta is a beta distribution with shape parameters 81 and 219. And it looks something like this. Okay, so this is the PDF of this. And so the numerator is the product of the likelihood times the prior. Okay, so this is the likelihood. This is the prior. The numerator is just the equivalent to the product of those two things. Okay, so I'm just going to take this theta raised to the 5th, 1 minus theta raised to the 5th, and I'm going to multiply it by the prior distribution. And for now, I'm just going to say the posterior distribution is proportional to it. Okay, I'm going to just say that it's proportional to the numerator. So because I'm saying it's proportional, I'm just going to ignore this constant here. Okay, this is just a constant. I'm going to ignore it, and I'm going to just say that it's proportional to this thing after I throw out the constant. Okay, and so overall, the numerator, or the posterior distribution, is proportional to the numerator, and I threw away all the constants, so I'm just getting the likelihood multiplied by the prior. Okay, and we'll notice that these two things, the likelihood and the prior, like they multiply nicely. Okay, these terms combine nicely. Okay, this is not always the case. When your likelihood function, which in this case is theta to the 5th, 1 minus theta to the 5th, and the prior distribution multiply nicely, we say that the prior and the likelihood, we call this distribution, we say that it is the conjugate prior. Okay, and you can, and maybe I'll throw in a slide with a link to Wikipedia, but basically the conjugate prior is going to be a probability distribution function, a PDF, that multiplies nicely with the likelihood function. Okay, so our data is a binomial random variable or a sequence of Bernoulli random variables. And the conjugate prior is the beta distribution. And we can see that if I use the beta distribution, which has this form multiplied by a constant, and I multiply it by the likelihood, we can see that these two things multiply nicely, that the terms combine nicely together, and I get this overall thing here, okay? And so we can say that the posterior distribution is proportional to this, okay? The posterior distribution is proportional to this. And in order to make it a PDF, all we have to do is we have to just make sure that we have to find the constant, the normalizing constant, so that this whole thing integrates to 1, okay? All right, so what is that normalizing constant? Okay, well, if we go back to kind of one of my earlier slides here, we said, you know, in the beta distribution, we know that the beta distribution, if we take the integral, it integrates to 1, and therefore we can establish that this portion will integrate to this. Okay, so we established this on an earlier slide, and so we're going to use that fact, and we're going to say, you know what, let's take the integral of this thing, okay? Because we said, so we said this thing is going to integrate to this, okay? So if I take the integral of this from 0 to 1, okay, this is going to be equal to the beta function with alpha equal to 86 and beta equal to 224, right? Because you know, we're taking advantage of the fact that from the beta distribution, we know that this thing has to integrate, that the entire PDF integrates to 1, and therefore this portion of the PDF integrates to this. Okay, so so is that okay? So therefore, the normalizing constant is going to be this function, and the PDF of the posterior distribution is going to be 1 over beta 86 224 and theta raised to the 85 1 minus theta raised to the 223. Okay, and maybe I'll just pause here and just make sure this makes sense and is good with everybody. I guess I'll go ahead and give you your second quiz answer for today. Second quiz answer is B as in bear, or B as in beta distribution, B. Is the second quiz answer, B as in bear, B as in beta. Okay. All right, and so the posterior distribution is equal to this, okay? And if we look at that, this is exactly a beta distribution, right? So a beta distribution has this PDF, okay? And this is exactly a beta distribution with shape parameters 86 and 224. Okay, so if our beta distribution is 86 and 224, this thing is exactly that beta distribution. All right, and so we can generalize kind of what we found here, and we can just say, in general, if your prior distribution on theta is a beta distribution with shape parameters alpha and beta, okay, that is that it has this prior distribution, and if your data comes from a binomial distribution or is equivalent to a sequence of n Bernoulli draws, then your likelihood is going to be this, right? So if you have a total of z successes and n Bernoulli draws, your likelihood is going to be theta raised to the z, 1 minus theta raised to the n minus z. And so the product of the beta distribution, which has this PDF, okay, the product of the beta distribution and the likelihood, if we just look at this portion, theta to the z and theta raised to the alpha minus 1, you know, it's going to multiply to be theta raised to the z plus alpha minus 1. And over here, this multiplied with this is going to equal 1 minus theta raised to the n minus z plus beta minus 1. Okay, So, I mean, this looks a little bit messy, but I'm just basically adding the numerators together. Okay, the numerator is n minus z and beta minus 1, and I'm just adding those two together. Okay, and this numerator is z, and I'm just adding this numerator. And so I mean, not numerator, exponents, right? So I'm just adding the exponents together, and I'm getting this, okay? And then again, the normalizing constant for this entire thing, just becomes, this messy constant over here. But again, it's just kind of established from the fact that, for the whole thing to integrate to 1, this is going to be the normalizing constant here. All right. Okay. And this posterior distribution is a beta distribution with alpha equal to the number of successes plus our original value for alpha, and beta equal to the kind of number of failures, n minus z, plus the original value for beta. Okay, sorry, give me a second. Okay, so overall, this is our beta distribution. Okay, this is summarized also in this Wikipedia page on conjugate priors. Okay, and it's basically saying that if your likelihood comes from either Bernoulli or binomial, and your prior distribution, the conjugate prior distribution is a beta distribution, and the parameters you use in your prior distribution are alpha and beta to just define your prior distribution. Then after you update it with the data you have seen, okay, the new parameters that you're going to get are going to be z plus alpha, which is expressed here as alpha plus the sum of the x's. Okay, so z for us is the total number of successes, which is the same as the sum of x. And beta is equal to beta plus basically the number of failures, which we can see here is n minus the sum of the x's. Okay, so n minus z. So we're getting the exact same thing that Wikipedia shows, which I guess is good. And also, as part of your reading this week for your homework, I'm having you guys read chapter 5 and chapter 6. And chapter 6, the authors, delve into this as well in great detail, and I think they do a good job there. Okay, so make sure you do your reading there. All right, so I just kind of wanted to show you some pictures to kind of show you how we can think about this. And we can think of the posterior distribution as a compromise between the prior distribution and the likelihood. Okay, so here is our prior distribution representing the prior distribution of the player's batting average. Okay, when we said this prior distribution just shows that everyone has a batting average over 0.2, most are below 0.3, and everyone's below 0.4 or 400. Okay, and so this represents our batting average. And we said our player had 10 at-bats and managed to earn 5 hits and 10 at-bats, okay? And so our likelihood is maximized at 0.5, okay? But again, 10 at-bats and 5 hits is not a huge amount of data, okay? 10 at-bats and 5 hits is not a huge amount of data, and so therefore, values of theta or p, or I think I use p in this thing, but you could have a theta of 0.7 and still get 5 hits and 10 at-bats. You can have a theta of 0.3 and get have 5 hits and 10 at-bats. Okay, and so the likelihood has this very broad kind of shape here. It's very wide. And the posterior is going to be kind of a compromise between the prior and the likelihood. Okay, and so if I put all three on the same plot, we can see that the prior distribution is this is in red, the likelihood is in blue, and the posterior is kind of a blend of these two, and it's just ever so shifted slightly to the right. Okay, so prior to looking at anything in the data, we had a mean of around 0.27, okay, 270. And then after seeing, kind of this very good performance of getting 5 hits out of 10 at-bats, okay, which is, equivalent to a batting average of 500, we adjust our posterior distribution to be a little bit higher to maybe have a mean of around 280, okay, 0.28. Okay, so it gets shifted a little bit to the right. Let me show you another example. Okay, let's say we start with the same batting average, okay, or prior distribution for the batting average, okay, beta distribution with shape parameters 81 and 219. But this time we're going to say this player has managed to sustain this very high batting average over 100 at-bats. Okay, so this would be a kind of a record performance. If a player was able to manage 50 hits and 100 at-bats, they would start making news headlines in the sports world. Okay, and so for this player, the likelihood, if you took frequentist statistics, the likelihood is maximized at 0.5. Okay, but again, we would say, this cannot be sustained for a very, very long time. Okay, this can't be sustained for a very long time. And so we're not going to say that this suddenly makes this player the greatest player of all time. Okay, even though 100 at-bats is a lot and 50 hits is a lot, and, this would, be kind of a significant event in the sporting world, we're not going to assume that this is going to be sustained for the entire season. Okay, and so the posterior is going to look something like this. And if I plot this all three together, we can see how the posterior has shifted a lot more. Okay, so the prior distribution was right here, kind of centered at around 0.27. The likelihood is centered at 0.5. And this basically, there's more data to back up this likelihood that's centered at 0.5. Okay, so this likelihood is centered at 0.5. And this likelihood is also centered at 0.5, but there's more data to back this one up, right? This one's based on 100 at-bats and not 10. And therefore, the posterior distribution is affected more. It shifts more towards this likelihood here, okay? Because we got more data to kind of back this up. And so this ends up being the posterior distribution. Okay, so here's another scenario. This prior distribution, I don't know what happened to, okay, this prior distribution is going to represent the prior distribution of a player who's had many at-bats. Okay, and so here I'm using parameters alpha equal to 405 and beta equal to 1095. Okay, so that the sum of alpha and beta is around 1500. And so this distribution has a mean of 0.27. It's got a lot less spread than, say, this prior distribution. So both this prior distribution and this prior distribution are both centered at 0.27, but this one has different shape parameters so that it's less spread and more pointy. Okay, indicating that we're more confident that this player's true batting average is a lot closer to 0.27. Okay, it's certainly not 0.33. It's certainly not 0.22 or something like that. It's very close to 0.27. So we're saying we're quite confident. So this could be, kind of a player who's been established in the league. We've been following his career, and currently his batting average is around 270. Okay, what would happen if the player has had kind of a poor performance over the last several games? Okay, so maybe in the last 100 at-bats, the player has had only 20 hits. Okay, we might say this player is in a bit of a slump. Okay, in that he's only batting around 200 in the last 100 at-bats. Okay, and again, batting below 200 is is not a good thing. Okay, in baseball. So in 100 at-bats with 20 hits, this would be the likelihood of the data. Okay, it would be centered at 0.2. That's the most likelihood. That's the value, the estimate of theta with the highest likelihood there. Okay. All right. The posterior, we will see, is affected only slightly. Okay, because this player, has kind of been established, has maybe had a long career running. And so we're very confident about his true batting average being around 0.27. So even though the player hits a bit of a slump, our posterior distribution, our distribution for this player's batting average is shifted only a little bit after seeing kind of 100 at-bats here. Okay, so it gets shifted only a tiny bit this way. Is that okay? On the other hand, let's say, oops, I don't know what happened here. Okay, let's say this slump is sustained for many at-bats. Okay, so we have the same player, same prior distribution. Oh, you know, I forgot to adjust the output size. And let's say this slump is sustained for a lot of at-bats, like 1,000 at-bats. Okay, so the players is just for the last, like, the entire season, his number of at-bat, I guess, well, let's see. Yeah, this would be like more than an entire season. Okay, so like for more than an entire season, he has a batting average of around 0.2. Okay, so there's now a lot of data kind of backing up that this is a long-running slump. Maybe it's not just a slump, but maybe it's more reflective of the player's performance. Okay, and so therefore the posterior distribution is a lot more affected. Okay, this represents the prior distribution. This represents what's happening with the slump, and so the posterior distribution ends up shifting quite a bit more towards the direction of all of the data that you have. Okay, and I don't have any examples of this, but the more and more data you collect, kind of your likelihood is going to have a smaller and smaller kind of amount of spread around the likelihood if you've collected a ton of data. And eventually it's going to kind of overwhelm whatever prior distribution or prior beliefs that you've had. And depending on how much data you've collected, the posterior distribution is going to look a lot more like the likelihood there. Okay, I'm not sure what happened with this lecture. I guess I went way faster than I did my first lecture. So I'm ending like 15 minutes early here. But did you guys have any questions regarding any of this? I hope this kind of makes sense regarding the relationship between the prior distribution, what happens in the likelihood that's reflected in your data, and the posterior being kind of a hybrid or a compromise between the prior distribution and the likelihood. So you'll be kind of messing around with this in your homework this week, and you'll be producing plots that are quite similar to this. And yeah, this very first homework is going to be more math heavy. Okay, this first homework is more math heavy because we're covering Bayesian concepts. We're not really doing any kind of Monte Carlo stuff. When we do Monte Carlo stuff, definitely you're going to have to incorporate computer programming to kind of do all of the random stuff. Okay, can I briefly explain the relationship between the beta and the binomial or Bernoulli? Yeah, so when we talk about the likelihood of the likelihood of data coming from a sequence of Bernoullis or a binomial distribution, the likelihood is going to look something like this. Okay, it's the probability of a success theta raised to the number of successes, and the probability of a failure, which is 1 minus theta, raised to the number of failures. Okay, this is going to be kind of your Bernoulli or your binomial distribution. The likelihood, though, so in a Bernoulli or binomial probability distribution, like the binomial distribution is discrete because the value that varies is the number of successes. And you say, well, what's the probability I get 5 successes? What's the probability I get 6 successes? What's the probability I get 8 successes? Okay, but the likelihood of a binomial distribution, you're treating the number of successes as fixed according to what you observed in your data, right? You observe a certain number of successes in your data. That's going to be the likelihood. That's going to be a fixed value. And in the likelihood function, the value that you're varying is the probability of success. You're varying this value theta. Okay, so theta can range anywhere from 0 to 1 because it's the probability of a success. And so the likelihood of a particular kind of sequence of data is going to be theta raised to some power and 1 minus theta raised to another power based on what you've observed in your data. So this is the binomial likelihood. Okay, and when you look at a beta distribution, the beta distribution is in this form, some constant times theta raised to a power 1 minus theta raised to another power. And so the beta and the binomial distribution have this property that when you multiply them together, they multiply very nicely together. Okay, they multiply very nicely together. And anytime you have kind of a situation where kind of the likelihood function for one distribution multiplies very nicely with another probability distribution, we call those things conjugate priors. Okay, so so Wikipedia has this nice long list of all sorts of distributions where if you have a Poisson distribution, okay, in a Poisson distribution, you look at kind of the likelihood in a Poisson distribution, it's going to multiply very nicely with the prior gamma distribution, okay? And then you kind of have the multi-categorical equivalent of a binomial and beta, which is the Dirichlet and the categorical or multinomial distribution. Okay, you've got other distributions like the normal distribution, and its conjugate prior is the normal distribution and things like that. Okay, and so this has a kind of a long list of all sorts of different data that appear, and the corresponding prior distribution that has nice properties of multiplication. I don't know. I hope that helps answer your question there. Okay, any other questions before I let you guys go? Did the likelihood of, okay, so question, did the likelihood of 50 out of 100, so 50 hits out of 100 at-bats, shift the posterior a lot more compared to the likelihood of 20 out of 100 since 0.5 was more different than 0.27? Okay, so these two are not exactly comparable because for this one, so we're looking at this, it shifted it a lot more. Well, it shifted a lot more because one is that the prior distribution was kind of broad. This was kind of like, this is the prior distribution before we saw this player do anything. So this was just kind of like, I'm picking a random player. We don't really know anything about this player to start with. And then we're seeing 100 data from 100 at-bats, okay? And so you'll notice that the spread for this prior distribution is somewhat wider, okay? Whereas over in this scenario, the prior distribution is very, very, very narrow, okay? Because we're saying that this is an established player that we know a lot about. And so, here we're getting 100 at-bats. And so it's going to shift it only ever so slightly, okay? If we kind of use the same prior distribution and we had 100 at-bats with 20 hits, yeah, it would shift it. And again, and you would be right that the shift would not be as dramatic because 0.5 is more different from 0.27 than 0.2 is from 0.27. So the shift would not be as dramatic, but it would definitely be more than this. The reason why this shift is very small, is just a tiny shift, is because this prior distribution is very skinny to begin with, in that we're kind of saying that we've established that this is a player whose batting average is very close to 0.27, and we're very confident about that. Okay, let me give you the last quiz answer for today. The last quiz answer for today is E as in elephant. E as in elephant. And that's it. Okay, any other questions? We good? We good to go? All right, so we'll end here for today. We'll see you guys on Friday. And yeah, you should be able to get started on your homework and make a good amount of progress. Make sure you read your textbook. Everybody's able to download the textbook, okay, right? I hope we've tried. Okay, so so that's great. I think it's a great book. And and if you had the actual version, there's like cute little puppies on the cover, which always makes you happy when you read the book. But alas, in the PDF, you kind of miss out on the puppies. All right, so we'll end here, and we'll see you guys on Friday.